So, exponential graphs, the parent function of that is y equals a times b to the x. And I'm going to explain kind of what each letter represents in a minute. We're going to start with, so x is your exponent in this case. So I'm going to start with y equals 3 to the x power. And I'm going to list these x values for you. And I want you to fill in the y's. So I've got -2, -1, 0, 1, 2, 3. And without graphing it, I just want you to fill in the y values. I'm going to give you a minute to do that. So if you're plugging in, it would be like 3 to the -2 power, 3 to the -1.
That's great.
So try filling those in. Let's fill them in. What is what's the y value for -2? 1/9. -1? 0? 1? 2? 3? Good. So let's just plot, let's start with 0, 1, because that's an easy one to plot.
Okay.
1, 3. 2, 9. And that's about as far as we can go. I don't even know where 9 hits.
It's above 1.
Okay, so right here. And then let's go in the other direction. So we've got -1 and 1/3. I'm just going to estimate. And it's approaching 0. So the 1/9 is really, really close. So if you go to -2 and 1/9, that's really, really close to 0.
So are we drawing a curve?
And yeah, so it looks like a curve.
Is it one of those like?
So where do you think there's an asymptote? Like what's it approaching?
Oh, the
-3 and x.
Not +3.
and 1.
No, so the line is getting closer, like on the left side, to what?
1/9.
0,
0, because it's 1/9. If I had -3, what would that be?
I don't know.
1/27. So it's getting very close to 0. So I've got an asymptote at 0. X equals 0.
Oh.
Now, let's talk about the domain and range of this. My domain for this graph is what?
Don't tell me.
-∞, +∞. So I'm going to say all real numbers. You could also write -∞ to +∞ if you want.
Left to right.
Yeah.
Gotcha.
Range,
Goes from
where's the asymptote?
0.
0. Does it touch 0 or does it just get super close?
No.
So parentheses 0 to infinity and beyond. Domain's left to right. Range is down to up. Bottom to top. Now's your time. To the x power, I'm going to give you the x values. And I want you to fill in the y's, graph it, and do the domain and range. So we're going to do same x values, -2, -1, 0, 1, 2, 3. I want you to fill in the y values, graph it, and then do domain and range. So here's what your graph should look like. Domain is all real, range is 0 to infinity, which is similar to the 3 to the x. So what do we notice about what happens on the graph above the x-axis? It curves. And what did we notice about where there is a horizontal asymptote?
0.
So the graph is essentially like approaching 0. So we could say that the graph levels off. So we have a horizontal asymptote. At y equals 0, because it is a horizontal line. What else do you notice about the y-intercept? It's always at 1. So we've got a y-intercept at 1. And why is that? What's the x coordinate in the y-intercept?
0.
0. Anything to the 0 power is 1. Right. So we're going to always have a y-intercept at 1 before, like, translating it left, right, up, down. So the parent function will always have a y-intercept at 1. Yes?
So which of the numbers is in this is 2a or b?
2 is b.
Would a be slope? And then what would be height?
We haven't talked about what a is yet, and we won't really do much with a in Algebra 2. It doesn't really get that until you get to pre-cal. So we mainly just talk about the b.
Okay.
And the b, in this case, is like how fast it's growing exponentially, kind of like the slope, but right now it's like saying 2 to a power. In the last example, it was 3 to a power, so that's growing exponentially faster, if that makes sense. But for right now, that is the b. We haven't looked at an a yet, and we won't do too much with it. Okay, let's sketch each of the graphs below without a calculator or without a table. So if we think about, why did it do that? Nope. If we think about a few of the points that we could plot, what is one that we could always start with? 0, 1. What do we know about the asymptote? It's going to be where?
0, 0. I mean, it's just
Y equals 0, so we can do a dashed line. What's another point that we could plot? 1, 5. I should have used green. And then I can connect the dots. What's it doing to the left? Curving towards 0.
So do we only need 2 points?
Mm-hmm.
Are you kidding me?
I'm not kidding you.
Okay.
Okay, number 4. This one is a decimal. So what's the first point I'm going to graph?
1.
0, 1. The next one is around 1, 8.
In the third.
Something like that. And I'm not going to be picky about it. I just want to,
Gets a ruler out.
yeah. I want to see the asymptote drawn. I want to see the point 0, 1. And from there, I'm not going to be picky about it.
It's pretty easy now.
Okay, since I have a pencil, can we just draw it like underneath, like right underneath the...
Okay, now we're going to look at the next example. And what do you notice about this number compared to what we've seen before? It's a fraction. So I'm going to give you the same x values as we've done before, and I want you to fill in the y values. So we've got -2, -1, 0, 1, 2, 3. So here's what happens when I have 1/2 to the -2. I'm going to draw it like this, actually. If I have 1/2 to the -2, what it's doing is it's first flipping that 1/2. So now the negative goes away. When I flip the 1/2, it's like saying 2/1 squared. And you don't really need the over 1. 2 squared is 4.
So why do you...
So the negative flips it, and then the squared squares it.
But I'm confused, like, when you flip it, how does that not take away, like, when it's x?
It just takes the negative away when you flip it.
So anytime we see a negative exponent, you flip it.
Yep. Anytime you have a negative exponent, you flip. 1/2 to the -1 is just 2. It's just flipping it. 1/2 to the 0 is still 1. Then 1/2 squared is 1/4. 1/2 cubed is 1/8. Okay, so let's graph it. Now, what do you notice about this graph? It's reversed. So, if I were to assign the the words increasing and decreasing to both of these examples. Would this one be increasing or decreasing? Decreasing. So this one is decreasing. Whereas, like the first examples we saw were more increasing to the right. This is decreasing. And later on we'll use the word like decay. But is the asymptote still the same? Yes. So the asymptote doesn't change. We've still got a horizontal asymptote at y equals 0. What about the domain and range? Does that change? Yes or no? Actually, no, it doesn't. So the domain is still all real numbers, because if I read it from left to right, and then range, bottom to top, the lowest it ever goes is 0. The highest is to positive infinity. So it's not changing, it's just changing directions, essentially. It's like I made it go decreasing instead of increasing. And why do you think that is? Because of the fraction, exactly. Because of the fraction. So if it's a fraction less than 1, it's going to be decreasing. If it's a number greater than 1, it'll be increasing. So that's kind of what these next questions are talking about down here. So how is the graph from example 3 different? We said that it's decreasing. Oh, that's a highlighter. How is the equation from example 3 different from the previous equations? Because it's a fraction. A fraction less than 1. So here we get into more of the a value. There we go. So the absolute parent-parent function, like the most simplest form, is y equals b to the x. Where if you have this number greater than 1, we consider that increasing. And if it's a number less than 1, like a fraction, but greater than 0, so basically a fraction, it is going to be decreasing.
What if b is equal to 1?
Then it wouldn't be exponential at all.
Okay.
Because if you had like 1 to the first power, 1 to the second power, it would just be a horizontal line at 1.
0 is less than b.
So if it's a number between 0 and 1,
Okay.
like a fraction, essentially. And we're going to apply our transformation rules. So we have to think back to all of our other graphs we've ever done, where we go left, right, up, down, and stretch, compress, all of that. And we're not really going to do too much of the stretch, compress with this. We're really just going to focus on the left, right, up, down, because that's all I really want you to get out of this chapter. So here's an example. We've got 2 to the x plus 3, and then minus 1. So horizontal shift, meaning left or right, is going to be connected to this x plus 3. So is it going to go right 3 or left 3?
Left 3.
Left 3. Good. And then up or down 1? Down 1. So since we have now gone down 1, that means that our horizontal asymptote has now also gone down 1.
Okay.
So instead of it being at 0, where's it going to be?
-1.
-1. So y equals -1. So we put a dashed line there. And I'm going to start, and if this is a transformation graph, the only thing I'm going to grade is 1 point.
Oh, great.
So the parent function starts at 0, 1, right? That's where I start. Then I go left 3, down 1. So I want everyone to make that point. Left 3, down 1. The new point is here. And so I'm going to erase this one. And will it be increasing or will it be decreasing? Increasing. So
Why was the
Why did you put the y-intercept at 1?
Because that's where the parent function starts at 0, 1.
Okay, but that's not for this graph.
No. So then we apply the transformations from 0. So we're starting point at 0, 1.
Okay.
Then we go left 3, down 1. And then it's increasing. So I just draw my graph like this. And I'm not going to plot any more points.
Wait, how do you know what parent function's good?
Because it's
'Cause
like
that's
the
where-
0 exponent,
Yeah.
and which means it's always at 1.
Like those first examples that we graphed, all of them were at 0, 1 because it had no transformations to it.
So whenever we did those like charts where it has like the
So this is like the original. I'm going to put it in a dashed line, 0, 1, like this. This is the original.
holy shit.
The dashed one is the parent function.
Oh.
Actually, no, it's not. It goes to 0.
I'm sorry.
Then we went left and down. So on the next graph, I want us to graph the parent function. Just do that in a dashed line. So a starting point, and then I want you to transform it. And don't worry about the b value. The only thing that tells me is whether it increases or decreases.
So if it's positive.
So because the last example was a 2 and this next example is a 4, I don't care about the number itself. I just care like what direction it's going in. So you don't need to worry about a second point.
So if the number is positive or negative, that's all you have to know.
Whether it's bigger than, like if it's a fraction or if it's a number greater than 1. Do what?
If it's just 4x and it's plus 2, it's not going
So this number itself is bigger than 1. So it's going to be increasing. That's what that tells me. So parent function, I'm going to do a dashed line like this.
Oh.
That's what I mean by increasing. Is that it's going up and to the right.
Yeah,
Now,
but you
what's
shift
the
that-
transformation?
You
Go
bring it up 2,
Up 2.
and then you draw that asymptote.
And where's the asymptote now? At 2.
Gotcha. That means it goes to the left.
Do we always have to draw the parent function?
If it says 2.
So if we went x1, it would be 1, 6 for this theoretically. If we have to plot a second point,
Yeah, I won't make you plot a second point on transformed equations.
So wait, what is it?
So what if it's negative? That's interesting. So the number itself is greater than 1. So it is still increasing, technically, the parent function is. But what does that negative make it do?
Is it flipped upside down?
It flips upside down. Perfect. So let's just draw the parent function, okay? Dash. My transformation is it does what? Left or right? Left 1. And what the negative makes it do is it makes it flip completely. So I've got this asymptote right here. If I flip it completely, that means that it's now, like imagine taking a pancake and just flipping it over the x-axis, okay? That's what it's having it do. So you always flip first. I want you to write that. Flip first, then go left or right, okay? So flip first, then go left or right. So imagine it flipping. Now the dot is right here. It's like a reflection. Then it goes left 1. So the dot is here at -1, -1. And it looks like this. So it's completely reflected the x-axis and it's gone left 1.
So how is that? Yeah, how is that still increasing?
at all.
Well, when you make it negative, it decreases.
So now it's decreasing.
But I don't want you to get caught up in the increasing, decreasing. Like, don't draw the parent function as is and then do the transformations. Do not get bogged down by the word increasing, decreasing.
Oh, okay.
So let's look at the number itself. This one, number 3. The number itself is 2. So the parent function is going to be increasing like this. Now I want you to transform it. So left, right, up, down. So what is the transformation? It's doing what?
Up 1, right 2.
Up 1, right 2. Where is my new asymptote? 1. Good. So I want you to try. Isn't that beautiful?
Can this be the test?
Does the asymptote just become that?
It went up 1.
Yeah.
Does it just become that number at the end?
Yeah, right?
Yes.
Like, as long as it's not the exponent.
Yeah.
Okay, so what I want you to try is 4, 5, 6 on your own.
Hey,
Yes.
I thought it was the same.
Number 6. Okay, so what I did is I flipped the x-axis first. So imagine here, I'm right here, I flip it, I'm now down here.
It's frozen.
No, it's not. I'm now down here. And I look like this now. I look like this now, right? So I flipped the pancake. Then I go left 2, up 2, and I'm here.
So why do you flip it? Because of the negative?
Yes.
This next question about
Okay, let's look at this next example. This is fun.
I feel like she made it.
What was your inspiration for the?
What was your inspiration for the example?
I think it was Anna.
No. This is all being recorded. Just want you to know that. So, at 7:30 a.m., the time in walks is misspelled. That needs to be fixed. And the time is not by coincidence at all that it happened at this time, because there are no rumors told at this time. But so 7:30 a.m., you walk into school and you heard a secret. Within 15 minutes, that person tells 4 more students.
Okay, so
Within another 15 minutes, everyone who knows the secret tells 4 more. So we can kind of see a pattern of this exponential growth happening, right? This continues until the entire student body knows the secret. Complete the chart below, where S represents the number of students who know the secret, and T represents the increment in 15 minutes.
I have a question.
Yes.
So within 15 minutes, they each, it should be just the singular person, right?
Well, yeah, that person, they tell 4 more students. I think it should be 5 more students, because we're doing 5 to the x.
Is there a limit to the student body? Or is it limited to the student body?
Do what?
Is there a limit to the student body?
We're just going to do to the 5th power. Okay, so we're going to say the equation is y equals 5 to the x. We're going to say that they tell 5 people, okay? So every 15 minutes, 5 people tell 5 more people, tell 5 more people, tell 5 more people.
But I thought it was
And it
4.
grows, right?
It's 4.
We're doing 5. I'm changing it to 5 because I like 5 better.
Buddy. Okay.
Work in progress. So 5 to the
What is
0
I?
power means that one person knows at time 0. 15 minutes pass by.
I am black.
They tell
Is that what that is?
5 people. So how many people know? 5.
What?
I just can't.
Oh, I got it now.
And the next one's 25.
25.
125.
125. 625.
Oh gosh, 2025.
3,125 people know. How many minutes has that been? So 15, 30, 45, an hour. An hour and 15 minutes. 3,000 people know.
It's not realistic.
That-
unrealistic. In about 30 minutes, 3,000 people.
That's like double our.
That's crazy. It's kind of like, have y'all heard that saying that's like, would you rather take $1 million or a penny that doubles every day for a
You
month?
take the pin.
You
every
take
day.
the penny. Yeah, it's interesting. So that's kind of this concept. So in
What is
an
the penny
hour
equal
and
to?
15 minutes, 3,000 people know. So let's graph this.
1, 2, 4, 6, or 8.
You've got 1, 5.
You get more than $1 million by the end of the month.
We've got 225 way up here. So here's what our graph looks like. And You can't really have negative time. It goes way up here. Now, is there ever a point, and so we're about to introduce something that I think is really cool. Is there ever a point where, like 22 people know? Is there ever a point in time?
I mean, yes,
Is there? Is there ever like an exact time where 22 people know, or does it just jump from 5 to 25?
It jumps from 5 to 25.
So we can kind of like estimate it, but according to this example, it's like after 15 minutes on the dot, they tell 4 more people.
Yeah, it's like they wait, they sit
And
there,
then
wait for
15
the
minutes,
voices,
so
and then-
it jumps from here to here to here. And we can technically like estimate when we think 22 people knew, but there's never ever a time when exactly 22 people knew. You should put on my desk. So what this is doing is, yes, it's an exponential growth, but it's kind of like a stepping stone. Okay, so it goes from 1, it jumps to 5, it jumps to 25, 125. And that space in between we're filling in, but it doesn't really exist in the time because the increment is every 15 minutes. Yes?
Okay, so when we look at the chart, right, so like 2 times at 0 minutes, 1 person knew, right? That
Yeah.
was IM. And then at 15 minutes, 5 people knew.
Yeah.
But if IM tells 5 people, then
That's
6
why
people
it's
knew.
4. I realized that's why we had 4. Because they tell 4 people.
So it would be y equals 4x, but then it
No,
would
5 to the x. So we're just looking at this. We're looking at this equation. 5 to the x.
No, but like how many people knew at 15 minutes?
5. 5 to the first power. 5 to the second
He
power.
tells 5 people.
Tells
and
4
he-
people.
Wait a second.
You're confusing me.
Yes. Yes. So it's just 5 to the first.
Like you tell 5, you tell 5, you tell 5.
Yes, if I tell 5 people, 6 people know.
No, we told 4 people.
Are you at 15 minutes or 0?
At 50, so
That's why it has 4. I was right.
2 cents on
okay, so he tells 4 people. So if we have
And so what this is, in the previous example, the base was 5. We're just going to fill this in. The base was 5. And the number of people who knew the secret jumped from 1 to 5 to 25 to 625. Oh, 125, sorry. And we could never figure out, like we don't know the exact time that 83.7 people knew the secret, but it's somewhere between 30 to 45 minutes, but we can't pinpoint an exact time. And 83.7 people isn't even an actual number because you can't have 0.7 of a person.
Sure, that's what you think.
And then what about 349 people? That could be somewhere between 45 to 60 minutes. But we just don't know. We can't tell because it jumps by a factor of 5 every single time. And then we just kind of create that smooth curve. We fill in the blanks. But with this number E, which is just a constant, like do y'all remember in geometry when you learned about this magic number pi? And it was 3.1415, keeps going. So that was like a magical number that determined the ratio between circumference and diameter, and it was just invented and just made up. Well, we have a new number that is invented that actually shows, this is really cool, it actually shows the natural growth where you could pinpoint the exact time breaking down every interval of every second. So, like if you were, have any of y'all like watched, like you've done like a slow-mo video of like the sun setting or something, and or maybe not slow-mo, but like a time lapse, yeah. And you see it like decreasing every second, every second, every second, every second. You could pinpoint at every second when that sun was setting, like what the height was or something. Or if you're watching a plant grow, if you were to watch it for 3 weeks every second, then it would hit every single height mark until it got to the point where it stopped growing. That's kind of what the natural base E is. If it's growing at a certain rate, if you put the base E there, it could pinpoint what every single second was naturally. So that's why it's called the natural base. So it, like if you have a base of 5, it has to hit increments. Like it hits at 1, at 5, at 25.
Okay.
If you have a base of E, which is this magic number, it hits at every single little point. Every point. And it doesn't take any breaks. It hits at every single second. It's like natural growing. It's really cool. So this is called a natural base E.
So how does that number? I just don't understand what that number randomly does.
I know, I don't understand either.
Who came up with this number?
I don't even know.
How can we know that we can?
So we write E to the X.
Avocado.
So when you come to think of E, think about pi. Like they're both constants. And we're going to think about E as 2.718. But we're going to write it as E. And you're going to use the letter E in your calculator.
Does this number ever stop?
So if E, like if pi is 3.14, no, this number never stops. Then E is 2.1, what was it? 2.71 or 72. Or you could do 2.718. I like that better. I just like that. So we're going to graph some of these without a calculator, and we're just going to estimate where 2.7 is, okay? So here we've got E to the X plus 2. No. We're still going to start with the 0.01, right? Because that's still like 2.7 to the 0 power is still what? 2.718 to the 0 power is still 1. So I'm going to start at 0, 1, and then the transformation is what? Up 2. So my graph still looks the same. And is E, does that mean that it's increasing or decreasing? Because 2.718, is that bigger than 1? Yeah. Yes, so that means that it is increasing. Okay, what about number 2? What would that do?
What we just did.
It's graphing it the same way. It's just like saying 2.718 here instead of E.
You have to reflect it first.
So I'm going to reflect it first. So here's my parent function. I'm going to reflect it first. Then I'm going to go left 1.
So when you say it hits every single second, do you mean it will hit every single point?
Mm-hmm.
So that means
Like along the curve.
okay. Along the curve, so this will hit.
It's like there's no stepping stone of like from 1 to 5. Like if you have 5 as a base, it hits in increments of 5.
Okay.
It hits every
Whereas
single digit,
it hits every single, it's like watching a plant grow and you like see it at every single height marker.
No, it's like there is no breaks.
Yeah,
It's
I think it's really.
an infinite number of points
Uh-huh.
between 1 and
Whereas like in a base of something else like 5 or 2, we're filling in the gaps.
So is it saying like whenever you square that number?
Mm-hmm.
So like if you keep if you go.
Okay, what would I do in number 3? Start at 0, 1.
Up 1.
Go up 1. And what? Right 2.
And that's your point.
Where you draw your point.
And where's my asymptote?
Guys.
1.
So, okay, so to draw the asymptote, you start at 0, 0.
Yeah.
Okay.
Okay, the last 3, I want to talk about these before the bell rings. We're kind of crunched on time. We've got 1 over E, okay?
Right.
Now, the only difference is that instead of increasing, 1 over E is like saying 1 over 2.7. It's now decreasing. So what does the graph, like the parent function, look like in a decreasing? It's opposite. I'm going to draw dashed. Well, this is just the parent function of it, so it is solid. So it's decreasing. So try 5 and 6.
Okay, so that means that it's exactly the same.
Left. And then this one would be right 3, down 4.
I need need the following to come to the front desk real quick. Christian Scaff, Ryan Patterson,